Welcome to The Explainer. Today we are going to break down what is arguably the single most important industrial process of the entire 20th century. Seriously, it's this incredible story of chemistry, of engineering, and, well, a huge dilemma that affects every single one of us. All right, let's get right into it. So here's the fundamental problem we're up against. The air all around us, it's almost 80% nitrogen. And nitrogen is absolutely essential for plants to grow, for life itself. But, and this is a big but, plants can't just breathe it in from the atmosphere. It's locked up tight in a form they just can't use. So how on earth do you solve a puzzle like that? The answer, it turns out, is a little molecule called ammonia, NH3. And really, this is the hero of our story today. See, if you can just figure out a way to snatch nitrogen from the air and smash it together with hydrogen, you can make an incredibly powerful fertilizer. You could quite literally make food out of thin air. That's the dream. Now, on paper, the reaction looks so simple, right? You take one nitrogen molecule, add 3 hydrogen molecules, and poof, you get 2 ammonia molecules. But here's the thing. Those nitrogen molecules in the air are unbelievably stable. They do not want to be broken apart. So trying to force them to react and to do it on an industrial scale, well, that's a whole different ballgame. It's a massive challenge. So what you end up with is this thermodynamic tug of war. To make this whole thing work efficiently, you've got to find the perfect, and I mean absolutely perfect balance of conditions. It really boils down to a series of brilliant but really tough compromises. Okay, let's tackle the first big compromise. Temperature. You'd think just crank up the heat, right? I mean, higher temps make reactions go faster, and faster is better for business. But here's the cruel twist. The reaction itself creates heat. So if you add more heat, the reaction actually starts going in reverse. It starts breaking the ammonia back down, giving you less of what you want. But if you go too cool, yeah, you get a great yield on paper, but the reaction is so painfully slow it's basically useless. So what do? You find that industrial sweet spot. After tons of trial and error, engineers landed on a temperature range between 450 and 500 degrees Celsius. It's this very specific, finely tuned compromise. Hot enough to get things moving, but not so hot that you kill your yield. It's all about balancing that need for speed with, actually making the stuff. All right, next up, pressure. Now, high pressure is fantastic for your yield. I mean, you're literally squeezing those gas molecules so close together, they have no choice but to react. The problem? Building and operating a factory that can handle that kind of insane pressure, well, it's not just complicated, it's dangerous. And it is ridiculously expensive. So once again, you've got a major trade-off on your hands. And that brings us to the second big compromise. The process actually runs at somewhere between 250 and 300 times normal atmospheric pressure. I mean, think about that. That is an immense amount of pressure. But that's the magic number. That's the critical balancing point that lets you maximize your ammonia output without making the factory so mind-bogglingly expensive that you could never afford to build it in the first place. But here's the thing. Even with all those carefully balanced compromises, the amount of ammonia you get from a single pass through the reactor, it's still pretty low. So how did they solve that problem? This is where the pure engineering genius comes in. The solution is something called the industrial loop. And this right here is the whole shebang. It's a totally closed loop system. Okay, so follow me here. The gases get pumped in, they react, and then the whole mixture gets cooled way down to about minus 33 degrees Celsius. Now, at that temperature, the ammonia you just made turns into a liquid, so you can just drain it right off. But the nitrogen and hydrogen that didn't react, they stay as gases. And here's the absolute genius part. You don't throw them away. You just pump them right back to the beginning of the loop to go through it all again and again and again. That simple act of recycling is what turns a pretty inefficient single pass into a ridiculously efficient overall process. It's brilliant. I mean, it's no exaggeration to say this process completely changed the world. It allowed the human population to literally explode. In fact, there's a pretty famous estimate that about half the people alive on Earth today, half of us, are fed by crops that were grown using fertilizer made from this exact process. But all of this incredible power, well, it comes at a pretty steep cost. There's a darker side to this story that we have to talk about. Look, being able to feed billions of people is without a doubt a modern miracle of science. But it forces us to ask a really uncomfortable question. What's the hidden price we're paying for all this? What's the environmental cost of this achievement? And here it is. For every single ton of ammonia we produce, almost 3 tons of carbon dioxide get pumped into the atmosphere. Now, where does all that CO2 come from? Well, it's mainly from 2 things. First, the process you have to use to create the hydrogen gas you need, and second, burning a whole lot of fossil fuels to generate all that crazy heat and pressure the reaction needs to work. Now, to put that number into perspective, just this one single industrial process is responsible for about 1.4% of all global CO2 emissions. Think about that for a second. One process. It's an absolutely staggering figure, and it just goes to show you the colossal energy footprint that's required to feed our planet. But here's the thing. Despite that massive environmental footprint, our reliance on this process goes way beyond just farming. It's not just about fertilizer. Ammonia has become really a foundational chemical for our entire modern world. I mean, this chemical powerhouse does so much more than just help grow our food. It's the starting block for making things like nitric acid and even nylon. It's used as a super powerful industrial refrigerant. It helps purify the water we drink and treat wastewater. It's even used in refining petroleum and stabilizing rubber. Seriously, its fingerprints are all over our daily lives. So when you step back and look at the big picture, what you have is the perfect definition of a double-edged sword. It's this brilliant yet incredibly complicated solution that solved one of our most fundamental human problems, hunger. But at the same time, it's a major contributor to another one of our huge challenges, climate change. And that leaves us with a really big question, maybe one of the biggest for the 21st century. We've got this one process that literally feeds the world, but also helps to warm it. It both sustains us and threatens us. So as we look ahead to the future of our food, our energy, and our planet, you just have to wonder, what's the next great compromise going to be?